So this is now 1.4. Inner product spaces. Normed spaces. And to the generalized distance, we will refer to as a metric spaces. So we can start right away with the definition of an inner product space. Now here, we will not, as I said, confine ourselves to Rn, to Euclidean spaces. We will start with some general real vector space. Let V be a real vector space. Now, what was, as a mathematical object, what was the usual inner product? It was a function on Rn cross Rn with values in R. You take two vectors, two n vectors, x and y, x dot y. What you produce out of that under this operation, that's a real number. So we'll define a generalized inner product as a function on V cross V, this is replaced by V, with real values which satisfies the list of properties IP1 up to IP5, this time modified to V instead of Rn. A function now I will use this strange symbol which looks like an emoji on V cross V with values in R is called an inner product if the following conditions are satisfied. Now here, if this stands for a function, this symbol, the functional notation usually is given a pair xy in here, then you write this O xy equal to some real number. But instead of that, for xy in V cross V, we will write this brackets xy for this functional notation. Okay? If this is for the function, if it's like f, then I'd write f of xy, but we'll use this. So we know the 5 conditions that we'll write. The first condition was for all x in V, the image of xx under this function that should be larger than or equal to 0. IP2 for all x in V, the image of xx under this function is 0 if and only if x is the 0 vector. IP3 for any xy in V, the image of xy under this function is equal to the image of yx. IP4 for all xyz in V, no matter what three members of V I take, the image of x taken together with y plus z, that is equal to the image of xy plus the image of xz under this function. Here, although we use the same symbol here, this is addition of real numbers, but this is addition of vectors in the real vector space V. Finally, IP5 for all xy in V and for all real numbers C. Now here, Cxy, that is equal to C times the image of xy. Now we had something further in our previous thing, that was here, you had that this is equal to x cy. Now we will not include this into the definition because this equality will follow from what we have assumed in here. Now let's check that, let's see that. Here, let's take x cy. Now by IP3, this is cyx. But then, by IP5, since this is for all xy, this is also for yx, cyx, this is IP5. But this is Cxy, and this is IP3. So this, by what we have up to this point, by those assumptions, by those conditions, this is equal to this. So this equality follows. So this would be redundant if I had included this into the definition. The definition would stay the same, but mathematically it would not be elegant. It would be ugly. Okay. Now let's continue this by defining a normed space. So V is a real vector space, and but before that, let me also write the following. When this is an inner product on V, we refer to V together with this inner product. Now V, of course, has plus and dot, the vector addition and scalar multiplication, but I will not write that. Whenever I refer to V as a vector space, it's automatically associated with those two operations as an inner product space. So Rn together with its usual inner product is an inner product space. We already know that. Now, a function, now this time for norm, well, the usual norm, that was a map which associated with each n vector a real number. So, well, this will now be replaced by a real vector space. Now I will use the same symbol on V with values in R is called a norm. If the following conditions are satisfied. Now here again, for x in V, we will write this customary notation. We will use this instead of. Now again, if this stands for a function, this symbol, then the image of x under this function, in the functional notation we use this, but we will use this. But the following conditions, we know what they are. For all x in V, x, the norm of x, that is to be the image of x under this map is supposed to be larger than or equal to 0. And 2, again, for all vectors x in V, the image of x under this map is 0 if and only if x is the 0 vector. And 3, given any x in V and given any real number c, the image of cx, which is again in V, that will be the absolute value of c times the image of x. And finally, N4, for all xy in V, the image of x plus y under this function should be less than or equal to the sum of the individual images of x and y respectively. As in here, when is a norm on V, we refer to as a normed space. Now, before we proceed to the generalization of a distance to the notion of a metric, let's ask the following question. When we had the usual inner product, we defined the usual norm in terms of that usual inner product. Now here we have a generalized inner product. If we take exactly the same formula to define, that is, if we take given any x in V, we consider the square root of the inner product of x with itself, well, we know that will be a norm because we wrote our proofs in the case of our n and usual versions of this, so that we can just take the picture of that and paste it as a proof. But let me first note that down. Now that will be a proposition. We start with an inner product space. So this automatically includes the real vector space structure of V. It's a real vector space endowed with an operation which satisfies the inner product properties. Now for each x in V, define this as the square root of the inner product of x with itself. Now, this is a norm on V referred to as the norm induced by this inner product. Proof, see above, replace Rn by V, the usual inner product by the inner product here, and the usual norm by the norm here. That yields the proof. Okay? But now the question is, the usual norm is induced by the usual inner product. Here we have the generalization of a normed space and an inner product space. In fact, if it were the case that each norm, in the generalized sense, were induced by some inner product on the same real vector space, then it would be strange to consider inner product spaces and norm spaces as if they were two different objects. They would be the same. An inner product space that would induce a norm space, that we know, that's always the case, but in that case, each normed space would also be an inner product space, and the norm would be induced by that. But of course, that's not the case. There are normed spaces where the norm is not induced by any inner product. So the notion of a norm space, that's much more general than that of an inner product space. Now let's see that. Now for that, well, we always go back to high school, to geometry. Let's do that again. Let us take a parallelogram and let's take its diagonals as well. How are the lengths of these two diagonals and the lengths of the edges of this parallelogram related to each other? Do you know This parallelogram identity, do you remember it from high school? Okay. Okay, well, vector geometry here is best to discover what's going on. Let me refer to this x. Well, in our case, this is x again, because what we do is we carry the end of the vector to the origin, then these are the same. So this is y, say, let me call this is y. Now, what will this be? This diagonal, that will be x minus, x, this will be y minus x. Now let me write it like this. Then it will be x minus y, and this diagonal, that will be y minus x. X plus y minus x, that's y. Then y, this is y, x plus y, I'm sorry. X plus y, and let me write this in this way as x minus y. Okay? Now, this is y, this is x, this is the sum, x plus y. Now this is y, this is x minus y, their sum is x. So the lengths of the diagonals, they're the norms of x minus y and x plus y in R2, the usual norm, and these are the norms of x and y respectively. So, having that in mind, let's write this. Now, but this time I will write what we will observe over there. We have not observed yet how these are related to each other for a general inner product space. Let V, together with this inner product, be an inner product space. Here, the rule is from geometry, the sum of the squares of these two diagonals is equal to the sum of the squares of the four edges. Well, you can easily see that when this parallelogram is a rectangle, then that follows from the Pythagorean identity. Okay, but that's in general true. Now that will become here as follows. For any xy in V, one has x plus y, this is the length of this diagonal squared, plus x minus y squared, that's this diagonal, its length squared. This is equal to the sum of the squares of four sides, but this becomes 2x squared and y squared. Okay? So this parallelogram identity holds in any inner product space, and its proof is very simple. Let xy be in V. Now, x, let me write this side, x plus y squared plus x minus y squared. Now here, where, let me write that as well. that's clear, but where this is the norm induced by the inner product here. We start with an inner product space, and here we use the norm which is induced by that inner product in this sense, okay? Okay, this is equal to what? Now, since this is induced by this, now this is just x plus y, the inner product of x plus y with x plus y, plus the inner product of x minus y with x minus y. But using the properties of the inner product, this part is just the inner product of x with x plus the inner product of y with y plus the inner product of x with y plus that of y with x, but they're the same, plus 2, why is this? But plus this, you have the inner product of x with x minus y, this becomes the inner product y with, then you have the inner product of x with minus y and minus y with x, but that's twice the inner product of x with y. So these two quantities, they get cancelled. But this is just the norm of x squared. This is just the norm of y squared. So you get this. So that's the proof of this identity. Well, now we'll use this. This will be a useful tool. Now, when we start with the normed space, in which this parallelogram identity is not satisfied, then it cannot be the case that the norm of that space is induced by some inner product on that space. Because if it were so, induced by some inner product, then this would hold. Now, let us then consider such an example. You have several examples in the first exercise set, both concerning inner products, generalized inner products, and generalized norms. One of them is the following on Rn. For each x in Rn, define, now I'll use here the standard notation for this. It will be a norm. We'll come back to this later. But this is defined as the maximum of the absolute values of all the components of x. So you take any n vector, you form the absolute values of the components and just the maximum. Now, is norm property 1 satisfied? Clearly so. Here you have a set of non-negative numbers. The maximum of that, that's non-negative. N2. Is N2 satisfied? Well, if x is the 0 vector, well, then you'll have here all zeros. The maximum of them 0, that's fine. If this quantity is equal to 0, well, then the maximum of all these absolute values, that must be 0. That means they're all 0, but then x1 up to xn, they all have to be 0. N2 is satisfied as well. Well, here, if you take Cx for some C in R, then its components are Cx1 up to Cxn. You take the absolute values of them. So this becomes the absolute value of C times the absolute value of x1 up to the absolute value of C times the absolute value of xn. But then the maximum of the exabytes, that will be multiplied in the end by the absolute value of C, which means that N3 is satisfied. It is N4, which is also easily seen to be satisfied, but let's go through that. Now let xy be two vectors. Now, this is equal to, by definition, the maximum of the absolute values of the components of x plus y. But now, the first component is x1 plus y1, the absolute value of that, then xn plus yn, the absolute value of that. But we know this absolute value that obeys the triangle inequality. Now let me replace this by a set but now this is larger than or equal to this. This is larger than or equal to this. Thus, the maximum of this will be larger than or equal to the maximum of this. Okay. I replace each term in here by something which is larger than or equal to that, so the maximum either stays the same or gets larger. But now, this clearly will be less than or equal to the maximum of x1, xn, plus the maximum of y1, yn. Now the maximum of this will be, for some I say, the absolute value of xi plus the absolute value of yi, this maximum. But the absolute value of xi, that will be less than or equal to this. And the absolute value of yi will be less than or equal to this. So this will be larger than or equal to this. So this will be x infinity plus y infinity. Thus, this is a norm on Rn. Now the question is, can this norm be derived, induced? Is there an inner product which induces this norm? Now let's just check that for R2. Well, let me take x equal to 1, 0, and y equal to 0, 1. We will see that these two xy's, these two vectors, they do not satisfy this parallelogram identity. But if that's the case, then there is no inner product inducing this norm. Because if that were the case, then this norm would satisfy the parallelogram identity. Now, well, then x plus y, that's equal to 1, 1. Then x minus y, I have that will be 1 minus 1. Now, this norm, well, that's the absolute, that's the maximum of the absolute values of this, it's 1. X minus y, well, the absolute values of this, they're both 1, so the maximum is 1. So this squared plus this squared, that's 2. But what about this? Well, 1, 0, the maximum is 1. Well, that's 0, 1, the maximum is 1. On the other hand, twice well, these are both 1, this is 4, but 4 is not equal to 2. So, is not induced by any inner product on, well, we have shown it for R2. Well, for R, of course, it will be induced by an inner product, okay, if this n is 1. Because it has just one component, you take the absolute value of that, and that's the usual norm. But we have shown it for R2, but in general, whenever n is larger than 1, this example can be easily extended to that. So that takes us to the brink of metric spaces. In fact, our main focus is on metric spaces, because the idea was to make precise when a point is arbitrarily close to a given set. But that, of course, requires something like a distance or like a generalized distance. So next time we'll start with metric spaces. So that will be the last item, the third item in here, but that will play the main role in what follows concerning the elementary topological properties of Euclidean spaces.